Hi children, welcome. Welcome once again to another chemistry class. Hope all of you are doing good, fine. Yes, today we are going to discuss some important questions from the chapter P block elements covering group 13 and 14. All of you know 11th standard P block elements covering group 13 and 14. Boron family, carbon family. A few important questions from that area. Chapter 11 of first standard, 11th standard topic. Can we start? Ready? Yes. First question, stability of +1 oxidation state increase in the sequence. You know the concept related. What is that? Yes, inert pair effect. Inert pair effect. Due to inert pair effect, down the group 13, 14, 15, 16, we find that down the group for heavy members, lower oxidation state is predominantly stable. You know that? Yes? So the answer is down the group, +1 state will be increasing. For group 13, all of you know there are two important oxidation states, that is +1 and +3. +3 is the group oxidation state. As you come down, +1 state will be predominantly increasing due to inert pair effect. So what is the answer? Option 4. Aluminium, gallium, indium, thallium. Aluminium, gallium, indium, thallium. All of you know aluminium will form AlCl3 where it is +3 state, where thallium will give you TlCl which is +1 state. Hope you understand. Next question. Boric acid is an acid because its molecule accepts OH minus from water releasing proton, combines with the proton to form from water molecule. No doubt, answer is option A. Boric acid is able to act as an acid. Why? Boric acid is acting as a Lewis acid. Boric acid is acting as a Lewis acid. It will accept OH minus from water. It will accept OH minus from water and it will produce H plus. You will get BOH 4 times minus BOH 4 times minus plus H plus. So it is acting as a Lewis acid. It is an aprotic acid. It's a weak acid. It's a Lewis acid. It's a monobasic acid. And the titration calculations are tough because of weak acid, and it can be enhanced by adding some polyhydroxy compounds like sugar, glycol, glycerin, etc. Think about that concept also, where it will act as a pretty strong acid. Why? Try to learn. Next. First choice. Third question. It is because of inability of NS2 electron of valence shell to participate in bonding that, once again, inert pair effect, due to inert pair effect, or inert pair effect is caused by inability of NS2 electron to take part in chemical bonding, right? Due to which SN2 plus is reducing while SN4 plus is oxidizing. Exactly, first choice itself is the answer. First choice itself is the answer. SN2 plus will act as a reducing agent while PB4 plus will act as a oxidizing agent. Why? Because PB4 plus is unstable. It will have a great tendency to come to PB2 plus. It undergo EC reduction and act as a very good oxidizing agent. And as far as SnCl2 etc. concerned, we are using even in organic chemistry for as an excellent reducing agent, right? Fine. So first choice itself is the correct answer. SN2 plus is reducing while PB4 plus is oxidizing. Right. Sn2 plus will be oxidized to Sn4 plus. Sn2 plus will be oxidized to Sn4 plus and hence act as a reducing agent. Right? Example, Stephen's reduction in learning in organic chemistry, 12th standard topic only. Okay. Which one of the following elements is unable to form MF63 minus? Why doubt? Boron. Why doubt? The first member of main group elements we know, they are unable to give the covalency beyond 4. Their maximum covalency limited to 4. Why? Because they don't have d orbital. They don't have vacant d orbital. That is the point. Right? So they have only s orbital and p orbital. Maximum covalency limited to 4. So you will not get BF63 minus. You can get the maximum BF4 minus. At the same time, you can get ALF63 minus. No doubt. So unavailability of vacant d orbital. That is the point. Okay. Next. Correct order of atomic radii in group 13 elements. Correct order of atomic radii. Atomic radii, how comes? Down the group, atomic radii increases. That's a trend. But when we look at group 13 element and the similar cases, you can find some sort of differences. Some sort of differences. Boron, aluminium, finding a trend. But aluminium, gallium, there is a difference. Gallium, indium, there is a trend. But indium, thallium, there is a difference. Why there is a difference? Because of aluminium, after aluminium, when you come to gallium, there is d orbital configuration coming. After gallium, indium, when you go to thallium, there is f orbital coming. That's why there is a difference in the atomic size and of course related all properties. Related all properties. You see the trend? It is boron, then gallium, then aluminium, then indium, and then thallium. It goes like that. Gallium, you see gallium, aluminium, 135, 143. Why? Because in gallium there is D10 configuration and the size will decrease due to poor screening effect. Okay. Yes. This is the area particularly we have to make a note of. A particular change we need to make a note on is gallium, aluminium. While thallium, you know, it is greater size but not to the expected level. That is happening because of f orbital configuration. So please have a look at the configurational difference. Boron, aluminium. Fine, there is a trend. Aluminium, gallium, you can find a difference because of D10 configuration. Gallium, indium, you find a trend. Indium, thallium, you find a difference. Okay, yes. Which of the following is incorrect statement? Which of the following is incorrect statement? SiCl4 is easily hydrolyzed. GeX4 is more stable than GeX2. SnF4 is ionic in nature. PbF4 is covalent in nature. That is a wrong statement. PbF4 and SnF4 both are ionic in nature. Fourth statement is correct. Both are ionic in nature. PbF4 and SnF4 both are ionic in nature. Refer text. Next. Which is not stable? Which is not stable? Another question from NCERT. Another question from NCERT. SiF6 can stabilize while SiCl6 cannot stabilize. And with the reason commented in the textbook, what is the reason? Due to the presence of d orbital silicon germanium, they can form this. But SiCl6 2 minus does not exist because 6th large chloride ion cannot be accommodated around the silicon due to the size. Due to bigger size of chlorine, we can see that it is not stabilizing. there is one more point referred in the NCERT. What is that? Electronic repulsion. So one is size of chlorine referred in the textbook. As a solved example, please find out that question and see why SiCl6 is not stabilizing. One is greater size of chlorine. Another one, due to that size and they are trying to come close. No, there will be a hindrance and quite naturally there is a electronic repulsion between the chlorine atoms. That is why it is not stabilizing. But SiF6, okay. Next. Correct order of basic strength is, option A, NiCH3 thrice, trimethylamine is more basic. Trimethylamine is more basic. This is trimethylamine. There is a lone pair of electrons significantly available. But you see that the case of triethylamine, it is coming like this. It is not sp3 tetrahedral. It is coming planar system. It is coming planar system. Why it is coming planar system? Because there is vacant d orbital in the silicon. And you can find the lone pair of electron with the nitrogen will be overlapping with the vacant orbital of silicon. The lone pair of electron with the nitrogen will be dispersing into the vacant orbitals of silicon. That is what happening. So what happens? The electron density on nitrogen will decrease. So it is less basic compared to trimethylamine. So the answer is option A. So there is a significant difference you must understand. And that is happening because of the vacant d orbital present with the silicon. And even there can be finding a partial double bond character due to the dispersing of electron also. Okay, next question. CCl4 not hydrolyzed by water, but SiCl4 is readily hydrolyzed by water because option C, carbon in CCl4 has no vacant d orbital, but silicon in CCl4 has vacant d orbital. Well explained in the textbook. This is SiCl4. This is SiCl4, and you can see water molecule will be interacting. Water molecule will be interacting with the vacant d orbital of silicon. Water molecule will be interacting with the vacant d orbital of silicon. That is what happening. So the hydrolysis is pretty easy as far as silicon chloride is concerned, but it's not so easy in case of carbon tetrachloride. Okay, next question. SiF6 2- is not, whereas SiCl6 not. This is because this is what the concerned question I was commenting earlier. From the textbook question, solved example. What are the points given? 6 large chloride ions cannot be accommodated. Already we have seen. Interaction between lone pair of chloride ion and Si4 plus is not very strong. That is the reason. Right? So, due to size, there is a steric factor and there is a lack of effective interaction. It was clearly explained in the textbook with the 2 reasons. Right? Next question. Decreasing order of enthalpy formation, graphite, diamond, fullerene. Graphite, you know, 0. Diamond is somewhat close to 2. And fullerene, what is the value? Some 30 something. That is the value. So the answer is option C. Option C. Decreasing order. Graphite, this is given in the increasing order. No problem. Option C, fullerene maximum, then diamond, then graphite. Graphite, enthalpy formation 0. Diamond, it is close to 2, 1.98. And fullerene, it is 38.1 kilojoule per mole. That value is also referred in the NCERT textbook. And this is the basis of taking graphite as thermodynamically the standard form, elementary form of carbon. Okay, next. Reaction of ammonia with the diborane gives. Another question picked from the textbook. Reaction of ammonia with the diborane gives. Initially you get this, which can be written like this, and the answer is option D. Whenever diborane react with ammonia, initially what you get? It can give several products. One of the famous product is borazine, borazole, the so-called inorganic benzene, and even it can form boron nitrides. Okay. But initially what you get? Initially what you get is B2H6.2 ammonia, which can be formulated correctly as option B. And the answer is option D. Option D. Interaction of BF3 with lithium borohydride. You get lithium fluoride plus X. X is diborane. X is diborane. B2H6, option B, diborane. Okay. Next. Antidote for CO poisoning. Antidote for CO poisoning is carbogen. Carbogen. CO is poisonous, everybody know, which can be used as a effective treating for that. Carbogen. Carbogen is a mixture of carbon dioxide with oxygen. Carbogen is a mixture of carbon dioxide with oxygen. Okay. It is 30% carbon dioxide and 70% oxygen mixture known as carbogen, used for treating people affected with carbon monoxide. Okay. Next question. The salts used to perform bead test. Salts used to perform bead test. Option A, borax bead test. Option A, borax bead test. Borax heated with a platinum wire loop, and strongly upon heating it will lose water of crystallization. Ultimately it is converted to a transparent bead-like form, which can be used for testing transition metals and their compounds. When placed a small quantity and when heated again, you get a colored bead, beautiful colored bead, and the color obtained will be according to the characteristic of transition metal. Okay. Answer is option A. And there can be one more answer. Suppose this one is like this. That also can be the answer. Sodium, ammonium, hydrogen, phosphate. That is called a microcosmic salt, which is not in the choice. Somebody who has read about microcosmic salt, there is a possibility of selecting option D, but it is not. This is microcosmic salt. Sodium, ammonium, hydrogen, phosphate. Microcosmic salt. An essential ingredient used in bead test. That also can give you bead test. So instead of borax, you can have a substituting component. That is nothing but the very famous microcosmic salt. Sodium, ammonium, hydrogen, phosphate. Okay. Next. Thermodynamically most stable allotrope of carbon, already commented. Graphite. Graphite is the thermodynamically most stable allotrope of carbon. As we know, enthalpy of formation arbitrarily fixed 0 for graphite. Okay. Next. Aqueous solution of borax is basic in nature, because borax is a salt of strong base and weak acid. Borax Na2B4O7, borax Na2B4O7 will hydrolyze. You will get NaOH and BOH thrice, that is H3BO3. So this is a salt of strong base and weak acid. That's why the aqueous solution of borax is basic in nature, alkaline in nature. Next, the starting material to prepare cross-linked silicones are linear silicones are produced by option C, R2SiCl2, where cross-linked polymers you can get by using RSiCl3. RSiCl3 can give you cross-linked polymer. Answer is option A. RSiCl3 can give you that. You see that RSiCl. Upon hydrolysis, what will happen? This chlorine will be replaced by OH group. And that OH group, when condenses with a different molecule, it can condense like this. And it can condense like this also. It is able to make a cross-linked character because there are 3 chlorine. And that upon hydrolysis you will get 3 OH group. And that can connect linearly as well as cross-linking wise. Okay. Next. Yeah, this is how it's happening. This is how it is happening. See that? 19th question. 19th question. CH3Cl silicon CH2SiCl2. You see that CH2SiCl2. That will give you linear polymer. Silicon polymers are obtained. You are getting silicon polymers option D. And this will give you, you see, R2SiCl2. Now you have 2 chlorine, which upon hydrolysis you get 2 OH group. Now what can happen? It can polymerize linearly over here. It can polymerize linearly over here. It will be polymerizing like this: CH3, Si, CH3, O, like this it goes. Like this it goes. And that is silicon polymers. Remember, silicon polymers, it can be made with a preparation of which requires several components. But to be precisely, R2SiCl2 gives what? Linear polymer. If you want to get cross-linked polymer, which one you want? RSiCl3 is required. While R3SiCl, you can use it for blocking the chain. R3SiCl, you can use for blocking the chain. Like that. So go through all those informations connected. Next question. From B2H6, all the following can be prepared except. You can prepare all except this. This you can't prepare. You see, diborane is a delicate molecule. Diborane is a delicate molecule. This is diborane. Four hydrogen atoms getting connected to the corner of the plane and 2 hydrogen atom connected here like this. Now the point is that you can replace this hydrogen with a CH3 group. You can replace this hydrogen with a CH3 group. You can replace this hydrogen with a CH3 group. And you can replace this hydrogen with a CH3 group. But you can't replace this. This you can replace, this you can replace, this you can replace, this you can replace. You can't replace this because it is somewhat like a bubbling bond, a banana bond, a highly delicate area. When you try to touch it, the molecule will be ruptured. You can't accept a CH3, expect a CH3 to be available coming like this. Sometimes it may happen with aluminum and all, but not here. You see, this you can't touch. So what you can replace this hydrogen, this hydrogen, this hydrogen, this hydrogen. 4 hydrogen atoms in the plane you can replace with a careful reaction. But you can't touch that banana bond. Banana bond is standing like this, all of you know. It's an adjustment bond. Okay, next one. So that is not possible. While you can get all other compounds, no issue. You can get, you see, one methyl group, two methyl group, three methyl group, four methyl group. That's it. That's it. Now you can get H3BO3, you can get NaBH4, no problem. You can get borazine. All these you can get, but not option C. Next question. At ordinary temperature, CO2 is a gas, but silicon dioxide is solid because option A, CO2 exists as individual discrete molecules. CO2 exists as individual molecules, but SiO2 forms joined molecules in which each silicon atom is tetrahedrally linked to 4 oxygen atoms and each oxygen atom linked to 2 silicon atoms. The structural details are available in the NCERT. The resonating structures of carbon dioxide given, silicon dioxide structures are given, all things are given there. Right? Next. The power of halide of boron to act as Lewis acid decrease in the order. Decrease in the order. BF3 is weak Lewis acid. Answer is option B. BBr3, BCl3, BF3. BF3 is weak Lewis acid due to back bonding. Due to back bonding, BF3 is a weak Lewis acid due to back bonding. BF3 is the weak Lewis acid due to effective back bonding. You see, there is back bonding in BF3. As all of you know, sp2 hybridized, one p orbital is free, while fluorine has p orbital with full of electrons, and it will migrate. It will merge, and due to which the electron density of boron will be minimized, and there is a partial double bond character between boron and fluorine. And hence, the electron density in boron will decrease. The Lewis acid character will decrease. Then why that is not effectively happening with the chlorine? Why that is not effectively happening with the chlorine? That is BCl3. The point is very simple. The point is very simple. You see, this is the difference. In fluorine, there is electrons available. Chlorine also electrons available. But the point is, here it is 2p orbital. This is also 2p orbital. Here, this is 2p orbital, while this is 3p orbital. There is an energy difference, size difference. So, effective back bonding does not take place. The effective back bonding takes place with the boron fluorine, due to which the electron deficiency on boron is compensated and it acts as a weak Lewis acid when compared. And hence the order option B. Clear? Next. BF bond length in BF3 is 130 picometer. BF bond length in BF4 minus is expected to be. It will be more than 130. It will be more than 130. You see, here it is 130. Here the bond length is 130 picometer. What will be the bond length in BF4 minus? It will be more than 130, because now there is no back donation. Now there is no back bonding because boron gets octet. So this bond length will be definitely, it is going to be definitely greater than, it will be definitely greater than 130. Which one? Only one choice. Only one choice, and it is option D, 143. See, if you don't know value 143, no problem. Only one choice is there. Here you have a back bonding. Here you have a back bonding. You see that. Due to back bonding, the bond length will be shorter. And now coming to BF4 minus, there is no back bonding. No need of back bonding because boron gets octet. I think it is okay. Fine. Next question. 24. Colaminate, sodium carbonate, HCl. You will get borax B on heating. It is not commented how much you heat. It must be option A. It must be option A. Let's have a look at. You see colaminate with the sodium carbonate, you will get borax. That is first compound. Oh, here A is missing. Okay, fine. Now, that A upon acidification, you get boric acid. That is B, boric acid. So, borax, boric acid. Now, upon strong heating to red hot, you will get boric oxide. First, you will get metaboric acid, then tetraboric acid. Finally, it is converted to red hot heating converted to B2O3. That is C. And now, that reacting with the magnesium, B2O3 will be reduced to metallic boron. Metallic boron can be obtained by reducing boric oxide with the magnesium. Okay. Next. Answer is option A. Producer gas, carbon monoxide and nitrogen. Carbon monoxide and nitrogen called a producer gas. Water gas, producer gas, etc. are important industrial fuels for various industrial processes. Next. Twenty-sixth question. Borax, H3BO3. That's the same question. We want to know the reagent 1 and 2. Borax upon acidification, you will get H3BO3. And you are getting this converted to boron. Already commented. Magnesium, option D. Magnesium can reduce B2O3 effectively to boron. There can be a confusion with aluminum also, but no problem. The better answer is magnesium. Magnesium can reduce B2O3 effectively to metallic boron. Already commented. Okay. Fourth choice is the correct answer. And the reaction already we have seen. Buckminster fullerene is made up of buckyball. All of you know 26-membered ring and 12 5-membered ring referred in the textbook, and the structural details are available. Made up of 26-membered ring and 12 5-membered ring. And keep it in mind, it contains hexagonal and pentagonal rings. Hexagonal and pentagonal rings. And what is the importance of this is, two hexagonal rings can come in contact. One hexagonal and one pentagonal can come in contact. See, this is hexagonal, this is pentagonal, hexagonal, pentagonal. Two hexagonal can be in contact. One hexagonal, one pentagonal can be in contact. But two pentagonal units will never be coming in contact. That is what the soccer ball structure. That is what the speciality of soccer ball structure. That's how Buckminster fullerene comes. Okay? Next question. A species that does not exist in free state. It is BH3. BH3 cannot exist in free state, and that's why it forms diborane. It is always available as dimeric form. B2H6. It is not available as BH3. It is available as B2H6. Dimeric form. Okay, next. The basicity of BOH thrice is. Monobasic. BOH thrice, the so-called boric acid. BOH thrice, the so-called boric acid. It is a weak acid. It is an aprotic acid. Already I have commented. Aprotic acid. It is a Lewis acid. It is a Lewis acid. And it is monobasic acid. Monobasic acid. And it's being a weak acid, the reaction is reversible and the finding of titration point is very tough, as I told. How can we determine the titration point clearly? How can we make it weak Lewis acid to act as a strong acid? That is what I told you to go through as a self-study. Okay. And the answer is monobasic acid. It is monobasic acid. Option A. Option A. It will accept a OH minus from this and it will become BOH 4 times minus and you will get H plus. Boron cannot form BF6 minus but can form only BF4 minus, while aluminum can form. This is because boron has a d orbital. No, boron has no d orbital. Aluminum has d orbital. Answer is option D. Boron has no d orbital while aluminum has d orbital. So it is with the help of d orbital we are able to extend the coordination beyond 4. Boron not having any d orbital while aluminum has. Okay. And that is the last question from the paper. Once again, we were trying to go through some important questions from the chapter P block elements covering group 13, 14 of the 11th standard topic P block. We will meet with another chapter, another few important questions in another class. Till then, bye. See you.